afternoon session. Our first speaker is Michelen, and he will talk about sampling theorems from the roots of generalizing.
Thanks for the invitation to the organizers, and thanks everyone for coming. So today I'm going to be talking to you about some recent and in-progress joint work with my friend Julian Zahazar-Boudet, who's currently at Cambridge. And this might be of a moderately different flavor. This will tell you how to transform information about the roots of probability generating functions into central limit theorems with very little effort. So hopefully this might be something where you can just hit some of your existing facts with these types of theorems and you'll recover some limit theorems. So first, what is a probability generating function? So if you're given a discrete random variable, and let's assume that it's bounded, we can define its probability generating function by just summing up the probability x equals k times z to the k. So you'll notice a couple of quick properties about this. I assume that x is bounded, so this guy is genuinely a polynomial, not like some long power series. The coefficients are non-negative. And in fact, when I plug in 1, we get 1. And if you're here, there's maybe a chance that you really don't care about random variables, but you do care about polynomials. So this could be your definition of a probability generating function. So really, this last condition is quite easy to make happen. You just have to divide by whatever scales it at 1 to make that occur. The real fact here is non-negative coefficients. So let's talk about a couple of properties. If you have independent random variables and you add them, then the generating functions just multiply. And by evaluating z to e to the I theta, we can relate the generating functions to the characteristic function or the Fourier transform. Characteristic function is what probabilists call the Fourier transform. I'll probably just call it the Fourier transform for the most part here, but I'll use them interchangeably. In particular, this means that this polynomial uniquely determines the distribution of x. So a quick review of some probability theory. So the characteristic function of a normal is just e to a polynomial of degree 2, where this first term is basically the mean, and the second one is the variance over 2. And we can define the cumulants of a random variable by just Taylor expanding the log of this moment generating function here. And you'll notice that having the third, fourth, fifth, and so on cumulants being identically 0 means that you are a normal random variable. These are, of course, different than the free cumulants, which we've seen earlier today. These are like the classical cumulants. And we, of course, also have the continuity theorem, which says that if you have a sequence of these random variables whose Fourier transforms converge, let's say to e to the negative theta squared over 2, then you get convergence of distribution to a standard normal. So let's start with a big fuzzy question. What is the relationship between these roots and the distribution of x? So let's start with a totally extreme case that's probably familiar to most of you, which is what happens if we assume that all of our roots are genuinely real? So since the coefficients are non-negative, all of these roots must be non-positive, so we write them as negative r1 through negative rn. And we can, of course, factor this guy. And you'll notice that we rescaled such that each of these linear factors is 1 at 1. And then we recognize that this is the generating function of a 0, 1 random variable with a certain probability of being 1. So we can decompose our original random variable with the sum of independent random variables that are 0, 1. And then if we hit this with an old-fashioned central limit theorem, like let's say the Lindeberg central limit theorem, when the variance of x is large, you end up with getting a random variable that's close to normal when I recenter and rescale. So let's talk here about an example of this. That this isn't just like some random toy case, as I'm sure most of you know. If you give me just a graph G, and you let mk denote the number of matchings with k edges, we can look at the generating function for these, and you end up with something real rooted. Of course, here I'm talking about like partial matchings. I don't need to have every vertex being hit. So this is a theorem of Hellman and Lieb, which has come up a couple of times so far here. And now this means that if we choose a matching uniformly at random, then provided the variance is quite large, the number of edges in this matching is going to be close to a normal when I recenter and rescale. So let's take it up a tiny bit and talk about a slightly more delicate case. So let's say we have a sequence of these discrete random variables. And suppose that there's some delta such that all the roots of all of my generating functions are no more than delta within 1. Sorry, no less than delta within 1. They avoid a disk of radius delta around 1. Let's assume also that our variance is bounded below by the degree of this polynomial to the 2/3. Then you end up with a central limit theorem. So you'll notice here that we're not adding up these random variables. It's the underlying random variables themselves that converge to normality. So this is a theorem by Leibowitz, Pittelrell, and Speer from 2016. I think it was on arXiv in maybe 2014. They are primarily interested in like spin state models, like certain facts about the Ising model, and also certain graph counting questions, which we'll come back later on. So in words, this says that having no roots near 1, together with this sort of mysterious variance condition, implies asymptotic normality. So why is this possibly true? You can still factor a polynomial over C. And now you'll notice these are linear factors where when I plug in 1, I get 1. Obviously, these are not probability generating functions, like they have complex coefficients, but we can still sort of pretend that they are. And the factor corresponding to a root lambda would correspond to some sort of random variable where the probabilities are defined by the coefficients of this polynomial. By probabilities, they're complex numbers, but they still add up to 1. And now this mass is complex valued, and the modulus of the mass for a linear factor is going to blow up as lambda approaches 1. So in some sort of vague, sketchy way, the idea is that if you have no roots near 1, you're convolving a lot of measures, none of which is much larger than the other, so believably you should get a central limit theorem of some kind. So that's all very hand-wavy. You can make that much more precise. So we can factor our polynomial. And now, if lambda is uniformly bounded away from 1, we can Taylor expand the log characteristic function of like one of these individual guys. And this big O term is going to be uniform, provided lambda is uniformly bounded away. And now when I add up all of those, I get log of the characteristic function for my original guy. And now I have a mean, and I have my variance over 2. And I still have this error term where now, since I've added up mn of these factors, I get a term of mn there. And now, when we renormalize, this term is going to go to 0, because I've assumed that mn divided by variance to 3/2 is going to go to 0. And that tells you that you get a central limit theorem. So OK. An interesting fact about this, which doesn't explicitly appear in the Leibowitz, Pittel, and et al. Paper, is that this works for all polynomials. And nowhere did we make use of non-negative coefficients. So if we all of a sudden define the mean of a polynomial to be what it would be if we had a generating function, sorry, if this were a probability generating function, and the variance the same way, we can say that a sequence of polynomials satisfies the central limit theorem if what would be the characteristic function converges to the characteristic function of a standard normal. So of course, I'm not making any statement about like what the coefficients are going to look like. You don't get to like use like the inversion theorem for Fourier transforms when you're no longer dealing with measures and you have signed measures. But they in fact prove that if you have a sequence of polynomials with roots uniformly avoiding 1 in the complex plane, and the degree is killed by variance to 3/2, then you get a central limit theorem in this sense. So this raises a question of what is up with this variance condition, right? What happens if we do make use of this non-negative coefficient stuff? So in about 2016, Robin P. Mantle conjectured that as long as you avoid 1 and your variance goes to infinity, you should get a central limit theorem. And it's worth mentioning that variance going to infinity is the absolute minimal possible condition you could have for this. Because if we have discrete guys and we're converging to something continuous, you have to be like normalizing out by something going to infinity. This was a touch optimistic, unfortunately. We're going to get to see just how it like barely misses. And Julian and I came up with a sequence of random variables that avoid 1, whose variance is on the order of log, but you have no central limit theorem. But Robin was correct that there is a significant amount of room to improve, but we have to think much more deeply about what it means to have non-negative coefficients. And I'm going to talk about that a little more at length. So what we show is if you have a sequence of these, you uniformly avoid 1, and now you just need that the variance is bigger than the degree to some fixed epsilon. For any epsilon that you give me, you get a central limit theorem. So to sort of recap this, having no roots near 1 implies normality or asymptotic normality, provided variance isn't subpolynomial in the degree. So the example that we have avoids 1 and has variance in the order of log, and this is a subpolynomial result, so they're very close to each other. We have some ideas about what the correct answer should be, but nothing super concrete. Okay, so let's philosophize a little bit. But what does it mean to have positive coefficients? So if I tell you a polynomial has positive coefficients, what information do we gain? So a basic fact is that none of its roots are positive. Just because if you plug in a positive number, you're not going to get 0. But obviously much more occurs. So here's a theorem that kind of encapsulates that. Just let's say that you give me a polynomial, and I'm telling you that the constant term and the top term are positive, just so we don't have to rescale it or anything like this. Then the following are equivalent. Having all sufficiently high powers having positive coefficients is equivalent to the linear and the trace term being positive, and having this condition known as strong positivity, which says that your polynomial is dominated by its value on the real axis. If I just like drag along the circle and hit the real axis. So why are we thinking about taking powers of this polynomial? Well, we're really concerned with roots of polynomials, and taking powers preserves the roots. And in fact, it does a little more than preserve roots. It even preserves the empirical measure of the roots, which is when you just put a point mass down at each place in the complex plane where you have a root. So this is really the best we can hope for if we want positive coefficients. Sort of thinking about what it means for all high powers to have positive coefficients. So you can sort of similarly ask, what happens if you want non-negative coefficients? And there was a conjecture by Bergweiler, Eremenko, and Sokol in about 2013, where they assumed that the linear and the trace term were 0. And they said, OK, let's suppose your bottom 3 and top 3 coefficients are positive, and you have the strong positivity condition. Then all sufficiently high powers have non-negative coefficients. So we showed this was true, and we in fact got the if and only if for having non-negative coefficients. And the point I brought this up isn't just so I can state another result. It's so that way this condition of being strongly positive is basically equivalent to powers having non-negative coefficients up to some sort of goofy combinatorial condition. There's also a result by Bergweiler and Eremenko sort of saying that the limits of polynomials with non-negative coefficients in some sense comes down to this condition. If you look at the empirical measure of these roots, so you just put a point mass down at each root, you ask what measures can be the weak limit of these, it basically comes down to just having this condition. So okay, how does this come into play for our case? So let's return back to random variables. So in the case of p being a probability generating function, this strong positivity condition is the same as the triangle inequality happening. Right? Just saying that the expected value of e to some complex number times x is less than or equal to the modulus, expected value of the modulus there. So this is going to imply a statement from probability, and some people might say harmonic analysis, which is that if you have a random variable and its Fourier transform is e to a polynomial, then the polynomial is of degree at most 2. So this is a theorem of Marcinkiewicz. I don't know if it's possible for a theorem to be classic and obscure, but this is. I don't know, this is a fantastic theorem, and when I first read it, I was offended no one told me about it before. It's pretty crazy. So having the third and higher cumulant all being 0 just by the definition of cumulants tells you you're a normal. But in fact, if I tell you the 10th and higher all 0, then this tells you you're still a normal. So the underlying fact that makes this all work is this triangle inequality. So the proof is a complex analysis type proof. I'm not going to really have time to get into it. But sort of the fact that makes it work and that doesn't work for signed measures is that the triangle inequality fails for signed measures, but is true for probability measures. So we use this to prove what's sort of like a compactness result. Right, and we say, okay, let's say you have a sequence of random variables, and we're looking at the cumulant sequence, and now these cumulants each depend on n. And if I tell you eventually that each of these cumulants converges n goes to infinity to 0, in some uniform sense that I won't get into, which is why this is a rough lemma, and you have some small cumulant that doesn't die, then you get convergence to a normal random variable. So I didn't want to write this out in like the full statement and like full rigor that it appears in our preprint, but this is sort of what the idea is that if you can show eventually all the higher cumulants converge then goes to infinity to 0, and you have enough control over how fast that happens, you can in fact get a central limit theorem out of it. So the idea is that if some lower cumulant, something like K3 through K9 or whatever, doesn't converge to 0, then I can rescale in a way such that I'll trap that guy. I'll end up with a limit that's e to a polynomial of degree strictly bigger than 2, but that's an impossibility by Marcinkiewicz. Okay. So let's perhaps see an example to graph counting. So our main theorem says as long as you avoid 1 uniformly, and indeed you have that the variance is bigger than the degree to some epsilon, then you get a central limit theorem. So here's an example of ours from combinatorics, which is, let's say you just have a sequence of graphs. You're going to choose a subgraph of max degree at most 4 uniformly at random. As long as the max degree of G doesn't grow too fast with respect to the number of edges, you get a central limit theorem. So a version of this was proved by Leibowitz, Pittel-Rell, and Speer, but they required the assumption that the max degree was bounded. So we get this extra room from upgrading this epsilon from 1/3 to just any epsilon. And also we have control over allowing roots to approach 1 at a specific rate. So let's perhaps give a bird's eye view of that. So the idea of this is to use subsequent iterative, Asano-Rule contractions. So if I give you, let's say, a 2-variable multi-affine polynomial, and it has no zeros in some rectangle, then the polynomial where I just squash these two down to a single z has no roots in some set I can control. So I imagine lots of folks here are much more familiar with this process than I am. But this gives us sort of a recipe for controlling roots. And of course, recipe should maybe be in quotes because everything has to conspire to go well in order for this to work. But you create a large multi-affine polynomial whose roots are easy to understand. You subsequently just squash down 1 variable at a time using Asano-Rule contractions. And each time you keep track of these roots. And at the end, you get a univariate polynomial whose roots you can control in a really sharp sense.
Can you say what the actual contraction is?
Oh, yeah, you're just mapping this polynomial to that polynomial. Oh, you mean in my case, in the graph counting one?
What's the map for if you have 3 variables?
No, it's just 2. So you just do this in each variable, mapping 2 of them down to 1, and you can then squash down this. So yeah, if you have 3 variables, you view it as multi-affine in 2 with coefficients also depending on the third, and you just keep going. There's also, to make this all work, but sort of doesn't fit as nicely in this half-live recipe, is an application of Grace-Walsh-Shago. Also happens, you make it all symmetric, so you get everything linear, and then squash them down iteratively. Yeah, any other questions on this? Okay, so we can generalize this a little bit to higher dimensions. As you guys know, there's a higher dimensional generalization of real rigidness known as stability, or real stability, which is when the polynomial is non-vanishing on the strict upper half plane. This is also an interesting experience for me because usually I talk to probabilists who have never heard this term, and now it's the exact opposite. You guys all know more about this than I do, but that's okay. So we can define the generating function of a multivariate random variable really similarly, where we just sum over the probabilities that it's equal to some vector times z1 through zd to that vector. And examples of such random variables include occupancies of determinantal processes, and we saw this also occur in the previous talk, sort of, a little bit. I'm sure you guys actually, in fact, have more examples than I do. Okay. Multivariate random variables with stable generating function satisfy central limit theorem under similar variance conditions to the central limit theorem of Leibowitz, Pittel-Rell, and Speer. And Ghosh, Liggett, and Pimentel in 2016 proved that if you have a sequence of random variables with stable generating function, and you have, let's say, the maximum term in your covariance matrix can rescale your matrix to some non-zero limit, and this variance is sufficiently large, you get a central limit theorem. I think there was a question in the last talk about whether or not there were Chernoff bounds for stable generating functions. I don't have one, but we do have a central limit theorem for them, which is in some ways similar. Yeah. Okay, so how does the proof work? The proof is like very nice and gentle. As is typical for multivariate central limit theorems, you almost always just reduce this to the univariate case. So a version of Kramer-Wold says that in order to prove that this rescaled guy converges in distribution to some normal, we just have to show that all linear combinations scale to the correct linear combination of the target distribution. So in fact, Kramer-Wold in its like generality for like all distributions says you have to check all projections, but for a normal, you can in fact check when you project just along vectors of positive integers. This is very lucky for us, because if I start with a stable generating function, and then I take a look at such a linear combination of its, if I take a look at such a projection, then the generating function of this projection is just plugging in z to some power for each of them. And now all I'm doing is you're taking the upper half plane, and you're squashing it down into some sector of the real axis, more or less. So stability is going to imply that Q has no roots in some sector. And therefore, Q has no roots near 1. And then you just have to hit this with the central limit theorem of Leibowitz, Padul, and Spear, and you're done. So luckily for us, we automatically get an improvement where now you just need this variance term to be bigger than n to the epsilon for some epsilon. Yeah. So the proof, of course, is the same exact thing. You just squash it all down. Okay. Went a little faster than I had intended, but that's okay. Candidates for examples of this would be really fantastic. We haven't thought too deeply about non-trivial examples, but if you guys have any examples of such things.
What do you mean by example here?
Oh, just random variables with stable generating functions that aren't like the handful that we always hear about.
Just curious, has somebody tried to use this convergence to that asymptotic normality to get some kind of maybe asymptotic version of van der Waals inequality for permanent, for instance? Because over there it's a probability of small ball.
Yeah.
Has somebody tried to do this? Do you have like good Essen-like bounds?
Sorry, good what bounds?
Like approximation, how you can, do you have nice control how you approximate?
Binormal? No, we don't. So we have none of this.
Essen-like,
No, none of this is at all effective. Yeah. Unfortunately. So part of the issue with that, yeah, so we would love to make this more effective and be able to look at things like that. Part of the problem with this Marcinkiewicz theorem is that it is like complex analytic in nature and thereby a little harder than usual to like effectivize. It's something that we are sort of working on, but we use analyticity of like, yeah, certain functions at various points, which means that like it's tough to make things approximate. But that is something we're trying to do. Yeah. But also to give a better answer to your question, we have not looked at that at all. Yeah. Any other questions? Yeah. And also, if you think of an example, you can just tell me anytime this week, or just in general. I'm always happy to hear more facts about this. So, okay. So, avoiding a neighborhood of 1, together with some mild variance condition, gives you asymptotic normality. What about criteria that doesn't have any variance condition, other than, of course, variance going to infinity? So an easy example, as we saw, was when all the roots are real. Right? You could just hit it with just Lindeberg's central limit theorem. And in fact, you do get an effective version. Like you do get a Barry-Essien type result there. Oh, and it's also worth mentioning, while that's coming up, Leibowitz, Piddle, and Spear do get a Berry-Essene type result. They do, in fact, have an effective version of that, which is quite nice. Okay. So there's another paper by Huang and Zakharovas, which deals with the case when all roots have modulus 1, so when they lie exactly on the unit circle. And this is equivalent to basically being symmetric, as in x is distributed the same as n minus x, and we also need the probability of 0 to be positive. They prove a whole bunch of stuff, but the most relevant, at least to this situation, is their central limit theorem. And they say that if your roots are all in the unit circle, then you get a central limit theorem if and only if the fourth cumulant converges to 0, which is the same as saying that the fourth central moment converges to 3. Their paper is really interesting and fantastic, but in some ways this is the least interesting aspect of it. They classify, in some sense, all possible limits of variables that have roots in the unit circle. And the proof here doesn't make use of non-negative coefficients. In fact, what it does is it directly manipulates the moment generating function and bounds higher cumulants in terms of certain sums of the roots, and then compares that to what happens to the fourth cumulant, and et cetera, et cetera. Again, I think the heavy lifting in their paper is, first of all, their insane list of examples, which is really fantastic, and also that they classify all possible limits. Okay, we have another central limit theorem, where if you give me a sequence of random variables, and suppose all the roots go to infinity at a sufficiently fast rate, then provided the variance goes to infinity, you get a central limit theorem. This also works when all roots go to 0 sufficiently quickly. You just have to replace xn by n minus xn, and that just flips everything from outside the unit circle to inside the unit circle. And the proof of this is you just express the cumulants explicitly in terms of the roots, and show that some low enough cumulant has to be large, which is the hard part here. And then you hit it with our version of this Martin-Kavitz theorem. So if you think about this in terms of this factoring over the complex numbers from a while back, right, this is really close to a Lindeberg central limit theorem because it's telling you that each individual point mass is very small. That's what it means for this root to go out to infinity. Okay. I have one more slightly strange central limit theorem. So let's say you define this region, and if you can't figure out what that looks like, it looks like that. If you avoid that region, you get a central limit theorem. So I'll go back to the region so we can talk about that. But in fact, we don't actually need all of the roots to avoid S for this to happen. We just need little o of the variance to 3/2 to avoid it, and all of the roots to avoid a neighborhood of 1. And then you get a central limit theorem. And this, in fact, generalizes the central limit theorem of Leibowitz, Piddle, and Spear. Let's take a look back at this. Yeah, there was a while when every time I gave this talk, I kept asking if anyone had seen this anywhere else in math. And I'm still looking for candidates, because I have not, but I think it's just some algebraic curve that is very specific to polynomials and variance. Okay. So I went, I think, a little fast, but that is all I have for you today, and thank you very much.
Plenty of time for questions.
Can you say anything about what properties of that curve
Yeah.
are the ones that
So yeah, let's kind of go back to the situation where we're factoring things. So if I factor, and we have real coefficients, so I can always pair them up by conjugate. Right, I mean, unless of course they're real. If I look at this dude, let's call it, let's say p lambda of z. I can associate a variance to this polynomial by pretending that this is a generating function of a random variable. And the variance of this guy is negative if and only if lambda's in that set. So sort of what it's telling you here is that the obstacles to being close to normal are when you have roots that contribute negatively to your variance.
So that region looks a little bit like the
region of zero-free region in the Riemann zeta function, and not by mistake, because you make all proofs following Adamov, the non-vanishing on the line 1. So instead of line 2, you'd have line 1.
Yeah.
Involve positivity of coefficients and trigonometric identities. And so the zero-free region for zeta is asymptotically like that. The part near 1 is a bit weird.
Yeah. Okay, yeah, I'll definitely take a close look at that. When I showed this to someone and they like immediately said folium of Descartes, which is like another algebraic curve, and it was unfortunately not that, but I will take a look at that.
It's not exactly that curve, but it's got the feature of this asymptote at 1 coming from positive coefficients.
Yeah. Oh, I understand what you're talking about. Yeah, I've seen this.
Right? You said something about measures, or maybe signed measures, on the circle, all whose roots are on the circle.
Yeah.
And all possible weak limits of those, what's the characterization?
So it's not signed measures, it's probability measures. It isn't a result I remember offhand, but the reference is Huang and Zakharovas. They talk about what the moment generating functions can look like.
And they have a complete classification?
Complete is perhaps a strong term, but they have some sort of characterization that is in some sense complete and not totally explicit.
In coding theory, people are very, in Gopa codes, you're familiar with those? Where you have the zeta function of a curve. In the curve case, in the right variables, all the zeros are on a circle. That's a Riemann hypothesis. And people have studied when the genus, so when the number of roots gets large, what are the possible weak limits, and nobody knows. There's some constraints that come from the positive coefficients, which are due to Ladut and Grunfeld, people like that. But I've never seen a classification, so I'm very...
Yeah, so it's not on the weak limits of the measures on the unit circle. It's on the underlying random variable associated to those polynomials.
Yeah, fine. Okay. That's where most of these zeros locate themselves.
Any other questions?
So is it necessary to assume that you're uniformly bounded away from 1 to your roots? Or could it be that they just go slowly?
Yeah, so if we have that the variance is bigger than n to the epsilon, then we just need delta to be bigger than, okay, this is definitely a don't quote me on that situation, but yeah, we just need it to be bigger than that. Yeah, so we can allow it to go to 0, just not faster than a certain rate. Oh, and here my double bigger arrow means little omega, so ratio going to 0.
All right, let's make this trip. So we need like 2:30, right?